Hey friends, it's Ben again. This is a video for the vector calculus class. We are launching into the notion of differential equations. Some of y'all had the differential equations class last semester. The actual planning for stuff would normally put you taking that course after this one, and so this would be a prelude. But, you know, these things happen. So with regard to this, we're going to look at some of the very basic stuff at the beginning here. What's it mean to have a differential equation? What's it mean to have a solution? There's a little more sophisticated thing that we'll allude to about when is your solution unique? When are you guaranteed to have a solution? So, all right, let's launch right into it and see where we go. Come on, connect. And it's not going to. Well, that was certainly thrilling while it lasted. So I am going to stall for a minute while I reboot my iPad and hope that it will reconnect the next time I do it. If it doesn't, then the stalling will be wasted, and this will be a really, I would advise you to fast forward to the portion of the video that actually has the iPad displaying something on screen. So in any case, the thing that we're looking at here, no, I'm going to pause. Okay, I've unpaused. Here's hoping that I can connect this time. All right. Screen mirroring. Touch. Yep. Okay. I have no clue when it's going to connect and whenever it doesn't. Sorry. All right, so our introduction to differential equations, the basic notion is that we are going to have something like dy dt, could be dy dx as well, but I often see a lot more of them that are dy dt. And then you have solved for it, and over here on the other side, you have some sort of f of ty. So it could be any function whatsoever, just anything. But it does have to involve both. Well, it can involve the independent variable and the dependent variable. We have looked at things in the past where you had, say, dy dt equals t, and you just integrated in order to solve it. But you can also have things more along the lines of dy dt equals, say, t times y. And then you can still solve it. It's just that you have to be a little bit creative about getting there. So the essential thing that we have to have though is that this function here needs to both be continuous, and its derivative with respect to y needs to be continuous across some sort of region. I've drawn it to be rectangular, but it can be patched together from multiple rectangular regions, even an infinite union of them. And it has to contain a point that we're going to be giving some initial value at. And so around that point, t naught, y naught, if the function f of ty and its partial with respect to y are both continuous, then we're going to be guaranteed, at least in the interval where we have that continuity, we're going to be guaranteed that we have some function y of t that satisfies our differential equation and our initial condition, right? So then the study of differential equations is really looking at, if you know that there's a solution, how do you figure out what it is? So we will be, with regard to our own, we will be looking at this for relatively nice techniques, but there really do turn out to be some things that you can't actually solve. You know there's a solution, but you can't find it. And for that, we have numerical techniques where we get approximations. But the key thing is you have to know a solution exists before you start approximating it. Because if you start approximating it and nothing exists, you'll get an answer anyway, and it may have nothing to do with what you wanted. So that's kind of our big deal here. So we're going to take a look at just one quickie example where we say, what's the largest interval where we can be guaranteed that this differential equation has a solution. Now, taking a look at that, you can see that it's not quite in the format we want. We need to go ahead and solve the y prime or the dy dt and end up with 1 over t square root of 4 minus t squared. So that divide by t there says we better not allow our t to be equal to 0. And then this portion here says that we have to have our t values be between -2 and 2. So then we take a look at what we're given, and we know that the t value of 1 is what we have to deal with this in. So if we're thinking about it maybe as a number line here, and we block off the -2 to 2, and then we also remember that at 0 we have some difficulties, then because we're having a solution where we have to look around t equals 1, then by examining the function we're dealing with, we know that we can't go any farther out than t equals 0 or t equals 2. And in fact, we can't include t equals 0, right? We could include t equals 2. So the interval that we're going to talk about would be 0 less than t less than or equal to 2, or if you prefer to write it the other way, parentheses 0, 2, square bracket. Okay, so that's what we're guaranteed out of that. Now, most of the time when you deal with a differential equation, you're going to look at it super quick and say, where are the discontinuities? Wherever the discontinuities are at, those are going to be the stopping points, and you're going to have your initial condition be between them. And once you've got that, you just figure that you can't take your solution any further. Okay. It may be the case that the solution exists in larger intervals, but there's no reason to think it will link up with the interval you've got. All right, so here's a little bit of mathematical modeling. It's a physics sort of problem that you've dealt with before. You know that in physics, we equate force equals mass times acceleration. And in particular, the acceleration that we're thinking about is going to be the derivative of a velocity function. So if we've got some sort of object in motion, then we're dealing with our force being equal to this mass times dv dt. So if you have an object that is dropped in a gravitational field, then you're going to equate mg and m dv dt and get dv dt being equal to g. And then depending on how that problem was set up, you're also going to have the other piece of information, v of 0 equal to, I said dropped, right? So that means that you drop it with 0 initial velocity. But if you're working with a projectile motion problem, then you've got an initial velocity, and so you're working with it differently. But with working that sort of thing out, you know, you can just integrate both sides on that and have your velocity at time t be equal to g times t, and I should say plus some v naught, but then you would plug back in over there and find out the v naught needs to be 0, and you'd have your v of t equals gt. So when you drop an object in a vacuum, and with certain other considerations that seem a little bit esoteric, about gravity being constant or whatever, but if you drop an object, then it accelerates smoothly, and that's that. Realistically, though, that's not what you've got. Realistically, you have your acceleration due to gravity, but you also have to think about your force being, I said mass times gravity, but then having that velocity be opposed by air resistance. There's some, we often use a gamma to represent it, but it could be whatever, some gamma times the velocity that is going in the opposite direction of the velocity. So that's air resistance. So in this case here, we've got this function of t and v showing up there, and you notice that the t doesn't even appear, and there is no problem with the v being under a square root or something like that. So really, for this problem here, that function that we're dealing with is going to be continuous for the whole real line, and that means that we can find a solution that works for all time. Now, there are some other considerations that you'll think of as esoteric, but from my perspective, not so much. If we talked about dropping that object and we had the air resistance or whatever, this function here isn't actually applicable for all values of t. It's only applicable for t greater than or equal to 0, right? Because prior to that, you hadn't dropped it. You were holding the object or whatever. So there do end up being some weird considerations sometimes. But this is a typical kind of modeling problem. So here's another sort of modeling problem. If you look at population dynamics, we frequently make the observation that a population grows in proportion to the population itself. If there are more people, then there will be more babies, and you can apply that to non-people populations as well. In particular, if you look at bacteria, often we will see this kind of growth happening with them as long as there is no limitation on resources. Once there gets to be a limitation on resources, it gets a little bit different, and we have to think about carrying capacity and things like that. But what we're going to do here is to take this function, and the p naught is a number, but we just don't have the value of it. It's something. And the r is a number. Again, we just don't know what it is. And we're going to show that we have a solution. So verifying that you have a solution to a differential equation is something that I don't know how often you'll actually do it, but it's good for you to be able to see what that entails. So if we're starting out with the p of t being equal to this, then we're going to have to calculate dp dt, and p naught is a constant. Derivative of e to the something is e to that thing, and then the chain rule says we'll pull an r in there, okay? And then if you look, that's r times the p naught e to the rt, so that is in fact equal to r times p of t. So that verifies that we have a solution to the differential equation, and then the initial value there, you just have to check and see that p of 0 is going to be equal to p naught e to the r times 0. So that's p naught. So that says that we have a solution to the initial value problem. As a matter of fact, I probably should have written, oops, I should have written the IVP here, okay? So let's maybe take a look at another one here. And this one's a little bit more complicated. This time we've got a second order differential equation. I have not formally defined this. I'm going to leave that to y'all to look at in the reading in the Trench textbook. But a second order differential equation has the second derivative in it. Third order differential equation, guess what? Yeah, okay. It does get confusing sometimes if you have a y prime that is then put to a second power. That's not y double prime. That's a nonlinear equation with y prime in it. Anyway, we're going to confirm that we have a solution here. And so the thing that we have to do is to get this stuff on the left-hand side and show that it's the right-hand side. Do not start by saying that you have a solution. Start by finding out if the thing you have is a solution, okay? That sounds like I'm being fussy, and I am, because it's something that people just don't listen to. So I'm going to calculate y prime. That'll be a e to the t minus b e to the minus t. And then I'm going to calculate y double prime, and that'll be a e to the t plus b e to the minus t, okay? Then I will calculate y double prime minus y is a e to the t plus b e to the minus t minus a e to the t plus b e to the minus t, which is 0, because you've got the cancellation here and the cancellation here, right? So when you're asked to show that something is a solution or to verify a solution, it really means take what it says on the left-hand side, show that it's equal to the right-hand side. Don't assume that it is, show that it is, okay? All right, so here we've got something where we're showing that we have a solution to an initial value problem. So kind of like the one earlier. So remember, we've got this here. And so now we have to calculate the dp dt portion of it. And that is going to be, let's see, the derivative of 900 is just 0 plus 100 times derivative of e to the t over 2 is e to the t over 2, and then times 1/2. And then that is 50 e to the t over 2, okay? And then there is the question, if you took 0.5, 900 plus 100 e to the t over 2, and then minus 450, would you get the same thing? So this is equal to 450 plus 50 e to the t over 2 minus 450. And we get the nice cancellation there. And so this is 50 e to the t over 2, and that was what we got for dp dt. So yes, we have a solution to the differential equation portion. Now we check p of 0, we're just plugging in here, 900 plus 100 times 1 is 1000, and that is in fact what we have here. So we have confirmed or verified or shown that we have a solution to that. Okay, is that right? The reason I'm asking is that people get super confused about this kind of problem when it's meant to be the easiest possible thing to do. People want to try to find the solution and say, aha, I found the solution and it was what you said it was. And then I have to ask, well, yeah, but, that's not what we were actually asking. So, all right, let's do one where we have to do the solution instead of having to verify. So we're just going the opposite direction on it. Now, notice that we don't have any x's on the right-hand side of the equation. That's good, right? Because we don't have any techniques for how to handle that yet. We will super soon, okay? But for right now, the thing that you'll do is to say your x of t needs to be equal to the integral of this 49 1 minus e to the minus t over 5 dt. So I will pull the 49 out front, and I'm going to integrate the 1 and get a t, and I'm going to integrate the minus a e to the minus t over 5, and I will have to then multiply it by a minus 5, the reciprocal of the minus 1/5. And then I'm going to put a plus c on the end, because those always show up when you integrate. So this is equal to 49t plus, oh gosh, 49 times 5. I think I'm going to just, well, okay, it would be 250 and then minus 5, right? Yeah, so 245 e to the minus t over 5 plus c, okay? And then you'd say, well, my x of 0 needs to be 49 times 0 plus 245 times 1 plus c, and I wanted that to be equal to 0. And that being the case, my c had better be negative 245. So my solution, x of t, comes back here to 49t plus 245 e to the minus t over 5. Wow, I wrote that super sloppy. And then minus 245. If you'd like to, you could take and group these two things at the end and factor out the 245 or something like that. But that is essentially what we're doing so far to find these. Now, if you're saying, hey, all right, that looks pretty easy. All I have to do is integration. Clearly, you don't remember Calc 2, because Calc 2 was a fearsome, horrifying set of integration where things could just go really, really badly. So we'll have some integration that's pretty rough to do. If you get stuck on it, go to Symbolab, go to Wolfram Alpha, get that to show you what to do. But be aware you're going to have an exam where you don't have those, right? So, all right. I'm going to leave it at that, and I will see you in class.